Why do some walls keep your home warm all winter while others seem to leak heat like a bucket with holes? You crank up the thermostat, the heater works overtime, but the warmth still escapes through the walls, through the windows, through the pipes. Here's a question that every engineer has to answer. How fast is heat escaping and how do we stop it? The answer lies in a concept so powerful, so elegant, that it completely transforms how engineers think about heat. And here's the fascinating part. It works exactly like an electrical circuit. That's right. Heat flowing through a wall behaves the same way electric current flows through a resistor. And once you understand that analogy, everything clicks. In this video, we're going to break down the complete physics of heat conduction. Through walls, we'll uncover Fourier's law, the master equation of heat transfer. We'll build thermal resistance networks, and we'll learn exactly how engineers calculate the overall heat transfer coefficient used in real buildings, refrigerators, and industrial pipelines. Whether you're a first-year engineering student or preparing for your exams, by the end of this video, heat transfer will feel intuitive, not intimidating. And if you're an engineering student who wants to truly understand concepts instead of memorizing formulas, subscribe to Academic Engineering. Hit that bell icon so you never miss a lesson. Before we can calculate anything, we need to ask a simple question. In which direction does heat flow? Heat conduction can happen in 1 dimension, 2 dimensions, or 3 dimensions, and this changes how we analyze it. Think about heat flowing through a window pane on a cold winter day. The temperature is different on each side, warm inside, cold outside. Heat flows in one direction, straight through the glass from hot to cold. This is one-dimensional heat transfer. The temperature changes only in the x direction. We ignore what happens at the edges. This is the simplest and most common approximation in engineering, and it's incredibly accurate for flat walls. Now imagine a long rectangular bar, like a structural beam, where heat enters from one face at 80 degrees Celsius and escapes from multiple faces at 65 to 70 degrees Celsius. Here, temperature varies in 2 directions simultaneously. This is two-dimensional conduction. It's more complex, but engineers use numerical methods and software to handle it. Now consider a refrigerator. Heat leaks from all sides simultaneously, top, bottom, front, back, and sides. Temperature varies in all 3 spatial directions. This is 3-dimensional heat conduction. For most practical engineering problems, we simplify to 1D when possible, and for steady-state problems where temperature doesn't change with time, this simplification is perfectly valid. Now, here's a key concept: steady-state heat conduction. In engineering, we often analyze systems that have reached a stable condition. The temperatures aren't changing with time. Heat flows in one side and out the other at the same constant rate. Mathematically, the energy balance for any wall is Q in minus Q out equals dE wall dt, where dE wall dt is the rate of change of energy stored in the wall. But here's the key insight for steady state. dE wall dt equals 0, because there's no change in temperature over time, no energy is being stored. This means Q in equals Q out equals constant. The rate of heat flowing through the wall is exactly the same everywhere, a constant value. This is why steady-state problems are so much easier to solve. Now we arrive at the most important equation in heat conduction, Fourier's law. Jean-Baptiste Joseph Fourier, a French mathematician and physicist in the early 1800s, gave us a beautifully simple rule. The rate of heat transfer through a material is proportional to the temperature gradient. In differential form, Fourier's law is Q cond wall equals negative K times A times dt over dx, where Q cond wall is the rate of heat transfer, watts. K is the thermal conductivity of the material, watts per meter degree Celsius. A is the cross-sectional area perpendicular to heat flow, meters squared. dt over dx is the temperature gradient, how fast temperature changes with distance. The negative sign is important. Heat flows from hot to cold in the negative direction of the temperature gradient. This ensures Q is positive when heat flows in the positive x direction. For steady-state, one-dimensional constant thermal conductivity conduction, we integrate Fourier's law across the thickness L of the wall. Integrating from x equals 0 to x equals L, Q cond wall times L equals K times A times T1 minus T2. Rearranging, we get the integrated Fourier equation. Q cond wall equals K times A times T1 minus T2 over L, where T1 is temperature at the hot face, degrees Celsius or Kelvin. T2 is temperature at the cold face, degrees Celsius or Kelvin. L is the thickness of the wall, meters. Assumptions. 1. Steady-state heat transfer, no change in temperature over time. 2. One-dimensional heat transfer, temperature varies only in the x direction. 3. Thermal conductivity K is constant throughout the material.
This equation is the foundation of everything we're about to build. Memorize it, understand it, and love it because we'll use it again and again. Here's the moment where everything becomes crystal clear. Remember Ohm's law from your electrical circuits course? I equals V1 minus V2 over RE. Current equals voltage difference divided by resistance. Now look at Fourier's equation again. Q equals T1 minus T2 over R cond. The analogy is perfect. Heat flow Q corresponds to electric current I. Temperature difference, T1 minus T2, corresponds to voltage difference, V1 minus V2. Thermal resistance, R cond, corresponds to electrical resistance, RE. Just as resistance opposes the flow of current, thermal resistance opposes the flow of heat. The higher the thermal resistance, the lower the heat loss. Thermal resistance is the ratio of temperature difference to the rate of heat flow. It depends on the geometry and the thermal properties of the medium. It's the heat insulation property of a material in a single number. Starting from Fourier's law, Q cond equals K times A times T1 minus T2 divided by dx. We rearrange to isolate the resistance. dx divided by K times A equals T1 minus T2 divided by Q cond. This ratio, temperature difference divided by heat flow, is the thermal resistance, so R cond equals L divided by K times A. And equivalently, R cond equals T1 minus T2 divided by Q cond, where L is the thickness of the wall in meters, K is the thermal conductivity in watts per meter times degrees Celsius, and A is the cross-sectional area in meters squared. Units, degrees Celsius per watt or Kelvin per watt. Think about what this formula tells us. A thick wall, a large L, has high resistance, harder for heat to flow through. A material with high thermal conductivity, a large K, has low resistance, heat flows through easily. A large area also reduces resistance. This is exactly how a resistor works in a circuit. More resistance, less flow. Simple. Now, in the real world, heat doesn't just conduct through a wall. On both sides of that wall, there's a fluid, air, water, oil, that carries heat away by convection. Newton's law of cooling describes this. Q convection equals H times AS times TS minus T infinity, where H is convection heat transfer coefficient in watts per meter squared times degrees Celsius, AS is surface area in contact with the fluid in meters squared, TS is surface temperature in degrees Celsius, and T infinity is temperature of the fluid far from the surface in degrees Celsius. Following the same logic as before, we define convection resistance. R convection equals 1 over H times AS, and equivalently, R convection equals TS minus T infinity over Q convection. Units are degrees Celsius per watt or Kelvin per watt. A high convection coefficient H means fluid removes heat very effectively, low resistance. A large surface area also reduces resistance. And here's the beautiful thing. This convection resistance is just another resistor in our thermal circuit. We can add it in series with the conduction resistance, just like adding resistors in series in an electrical circuit. Now, let's assemble the complete picture. In a real building wall, 1. Warm indoor air transfers heat by convection to the inner wall surface, T1. 2. Heat conducts through the wall from T1 to T2. 3. The outer wall surface, T2, transfers heat by convection to cold outdoor air, T infinity 2. This is exactly 3 resistors in series, just like 3 electrical resistors connected end to end. R total equals R convect 1 plus R conduct 1 plus R convect 2. Expanding each term, R total equals 1 over H1 times AS plus L divided by K times AS plus 1 over H2 times AS, where H1 and H2 are the convection coefficients on the inner and outer surfaces respectively. The thermal circuit is visually identical to the electrical circuit, 3 resistors in series between 2 temperature nodes, just like 3 electrical resistors between 2 voltage nodes. This is the power of the electrical analogy. Once you draw the thermal circuit, you can analyze it exactly like a circuit problem. With the total thermal resistance known, the rate of heat transfer through the wall separating 2 media is Q dot equals T1 infinity minus T2 infinity divided by R total. This is the overall temperature difference from fluid to fluid, divided by the total resistance. Elegant and simple. Engineers often express it as Q dot equals U times A times delta T, where U is the overall heat transfer coefficient, defined as 1 over A times R total. Units, watts per degree Celsius or watts per Kelvin. The overall heat transfer coefficient, U, captures everything, conduction through the wall and convection on both surfaces in a single number. Engineers use U values to compare the thermal performance of building materials, windows, and insulation systems. A low U value means good insulation. A high U value means heat flows easily, bad for an energy-efficient building. So far in this series, we've covered all the essential theory behind conduction and convection, the governing equations, the concept of thermal resistance, and how heat flows through composite walls. Now it's time to put that theory into practice. We're going to solve 2 complete problems on mixed-mode heat transfer, step by step, just like we would in a real exam. Let's get started. All right, let's read the problem carefully. We have a glass window, 0.8 meters high and 1.5 meters wide. The thickness of the glass is 8 millimeters, and its thermal conductivity, K, is 0.78 watts per meter Kelvin. The indoor room temperature on the inside is 20 degrees Celsius, and the outdoor temperature is negative 10 degrees Celsius, so heat is flowing outward from the warm room to the cold outside. Now, the problem also tells us the convection coefficient on the inner surface, H1, is 10 watts per meter squared Kelvin. This represents natural convection inside the room. The convection coefficient on the outer surface, H2, is 40 watts per meter squared Kelvin. This is the forced convection due to wind outside. And importantly, radiation effects are included. Now, what are we asked to find? First, the steady rate of heat transfer through the window, Q dot, in watts. Second, the temperature of the inner glass surface, T1, in degrees Celsius. This is a classic mixed-mode problem. We have convection on both sides and conduction through the glass in the middle. The key tool we'll use is the thermal resistance network. Now, the screen divides into 3 columns, given data on the left, the solution in the center, and the calculations on the right. Let's work through each step. On the left, let's confirm everything we're working with. Height h equals 0.8 meters. Width W equals 1.5 meters. Thickness L equals 8 millimeters, which equals 0.008 meters. Thermal conductivity, K, is 0.78 watts per meter Kelvin. The indoor fluid temperature, T infinity 1, is 20 degrees Celsius, and the outdoor fluid temperature, T infinity 2, is negative 10 degrees Celsius. So heat is flowing outward from the warm room to the cold outside. Now, the problem also tells us inner convection coefficient, H1, is 10 watts per meter squared Kelvin. Outer convection coefficient, H2, is 40 watts per meter squared Kelvin. Good, everything is noted. Now let's begin solving. The very first thing we need is the surface area of the window. This is straightforward geometry. The formula is simply AS equals H times W. Substituting the values, AS equals 0.8 times 1.5. AS equals 1.2 meters squared. Simple, but important because this area appears in every resistance calculation that follows. Now let's build our thermal resistance network. Think of it like an electrical circuit. Heat flows through resistances in series, one after another. We have 3 resistances in this problem. First, convection resistance on the inner surface. R-conv1 equals 1 divided by H1 times AS. This resistance represents how difficult it is for heat to transfer from the warm room air onto the glass surface. Substituting 1 divided by 10 times 1.2. R-conv1 equals 0.08333 degrees Celsius per watt. Second, conduction resistance through the glass. R-cond equals L divided by K times AS. This is the resistance offered by the glass itself as heat conducts through its thickness. Substituting 0.008 divided by 0.78 times 1.2. R-cond equals 0.00855 degrees Celsius per watt. Now observe carefully. This value is extremely small. That tells us the glass itself offers almost no resistance. The dominant resistances are the convection layers. Third, convection resistance on the outer surface. R-conv2 equals 1 divided by H2 times AS. This is the resistance from the outer glass surface to the cold outdoor air. Substituting 1 divided by 40 times 1.2. R-conv2 equals 0.02083 degrees Celsius per watt. Now, since all 3 resistances are in series, the heat must pass through each one in sequence. We simply add them. R total equals R-conv1 plus R-cond plus R-conv2. Substituting 0.08333 plus 0.00855 plus 0.02083. R total equals 0.1127 degrees Celsius per watt. This is the total opposition the entire window system offers to heat flow. Excellent. Now we can find what we came for, the steady rate of heat transfer, Q dot. From Newton's law of cooling applied to the entire resistance network, Q dot equals T infinity 1 minus T infinity 2 divided by R total. The temperature difference is 20 minus negative 10 equals 30 degrees Celsius. So Q dot equals 30 divided by 0.1127. Q dot equals 266 watts. This is the rate at which heat is escaping from the warm room to the cold outdoor environment, 266 watts, continuously on a steady basis. That's quite significant for a single window. Now for the second part, finding T1, the temperature of the inner glass surface. The idea here is simple. As heat flows from the room air at 20 degrees Celsius through the inner convection resistance, there must be a temperature drop. The inner surface temperature is lower than the room air temperature. The formula is T1 equals T infinity 1 minus Q dot times R-conv1. Substituting, T1 equals 20 minus 266 times 0.08333. T1 equals 20 minus 22.17. T1 equals negative 2.2 degrees Celsius. Now, isn't that striking? The room is at 20 degrees, but the inner glass surface is already at negative 2.2 degrees. This is exactly why windows fog up and frost forms on the inside. The glass surface is well below the dew point. So let's box our final answers for problem 1. Q dot equals 266 watts, the steady rate of heat loss through the window. T1 equals negative 2.2 degrees Celsius, the temperature at the inner glass surface. Well done. That was a clean, systematic application of the thermal resistance method. Now let's move straight into problem 2. All right, problem 2. Now we're looking at something a little more complex, a refrigerator. The interior has a base area of 0.5 by 0.5 meters and a height of 1.0 meter, and it must be maintained at 6 degrees Celsius. The walls are a composite structure, not just one material, but 3 layers. 2 mild steel sheets, each 3 millimeters thick, with K equals 46.5 watts per meter degrees Celsius. These are the inner and outer metal skins of the fridge. Between them, 50 millimeters of glass wool insulation with K equals 0.046 watts per meter degrees Celsius. This is the critical layer that keeps the cold in and the heat out. The kitchen surrounding the fridge is at 25 degrees Celsius. The average convection coefficients are H outer equals 11.6 watts per meter squared degrees Celsius on the kitchen side surface, H inner equals 14.5 watts per meter squared degrees Celsius on the inner refrigerator interior surface. What do we need to calculate? First, the rate at which heat must be removed from the refrigerator interior to maintain it at 6 degrees Celsius while the kitchen is at 25 degrees Celsius. In other words, how hard does the compressor need to work? Second, the temperature on the outer surface of the metal sheet facing the kitchen air. Notice this problem has 5 resistances in series: outer convection, outer steel sheet, glass wool insulation, inner steel sheet, and inner convection. Let's work through them carefully. Again, the screen organizes itself into 3 columns. Let's go column by column and step by step. On the left, the given data is listed cleanly. Base equals 0.5 by 0.5 meters, height equals 1.0 meter, T inside equals 6 degrees Celsius, T kitchen equals 25 degrees Celsius, LA equals LC equals 3 millimeters, the 2 steel sheets equal thickness, K steel equals 46.5 watts per meter degrees Celsius, LB equals 50 millimeters, glass wool, K wool equals 0.046 watts per meter degrees Celsius, H outer equals 11.6 watts per meter squared degrees Celsius on the kitchen side surface, H inner equals 14.5 watts per meter squared degrees Celsius on the inner refrigerator interior surface. Perfect. Now let's begin. Before we do anything else, we need the total surface area of the refrigerator through which heat enters. The fridge has 2 types of surfaces: top and bottom, the 2 base faces, 0.5 by 0.5 times 2, 4 sidewalls, 0.5 times 1.0 times 4. So, A equals 0.5 times 0.5 times 2 plus 0.5 times 1.0 times 4. A equals 0.5 plus 2.0. AS equals 2.5 meters. This is the total area through which the kitchen heat is trying to leak into the refrigerated space. Now this is the key step. We have 5 layers in series, so the total resistance formula is R total equals 1 over AS times 1 over HO plus LA over K1 plus LB over K2 plus LC over K3 plus 1 over HI. Let's substitute each term carefully. 1 over HO equals 1 over 11.6 equals 0.08621. LA over K1 equals 0.003 over 46.5 equals 0.000645. The outer steel sheet, almost negligible. LB over K2 equals 0.05 over 0.046 equals 1.0870. The glass wool, by far the dominant resistance. LC over K3 equals 0.003 over 46.5 equals 0.000645. The inner steel sheet, again negligible. 1 over hi equals 1 over 14.5 equals 0.06897. Now, observe carefully. The glass wool alone contributes 1.087 out of the total. That's the entire point of insulation. The steel sheets are essentially transparent to heat. Adding all terms, 0.08621 plus 0.000645 plus 1.0870 plus 0.000645 plus 0.06897 equals 1.2423. Then, dividing by AS equals 2.5, our total equals 1.2423 divided by 2.5 equals 0.497 degrees Celsius per watt. Now, applying the thermal resistance formula, Q dot equals T infinity 1 minus T infinity 2 over R total. The temperature difference here is from kitchen to interior. 25 minus 6 equals 19 degrees Celsius. Substituting, Q dot equals 19 over 0.497. Q dot equals 38.23 watts. This means the refrigerator compressor must continuously remove 38.23 watts of heat from the interior just to counteract the heat leaking in from the kitchen. This is the minimum cooling load on the system. Finally, be find T1, the temperature on the outer metal surface of the refrigerator wall facing the kitchen air. As heat flows from the kitchen air at 25 degrees Celsius through the outer convection resistance, the temperature drops before it even reaches the metal surface. The formula is T1 equals T infinity 1 minus Q dot times R convection outer, where R convection outer equals 1 over HO times AS. So, T1 equals 25 minus 38.23 times 1 over 11.6 times 2.5. T1 equals 25 minus 38.23 times 0.03448. T1 equals 25 minus 1.3183. T1 equals 23.68 degrees Celsius. After simplifying, the outer metal surface is at 23.68 degrees Celsius. The kitchen air is at 25 degrees Celsius, so the temperature drop across the outer convection layer is only about 1.3 degrees. Most of the temperature drop from 23.68 all the way down to 6 degrees happens across the insulation layer. That is the power of glass wool. So our final answers for problem 2 are Q dot equals 38.2 watts, the steady rate of heat that must be extracted from the refrigerator, and T1 equals 23.68 degrees Celsius, the temperature on the outer surface of the refrigerator wall. And there we have it, 2 complete problems solved from start to finish using the thermal resistance method. Now let's step back and appreciate what we've built today. We started with a simple question: why do some walls lose heat faster than others? And the answer turned out to be one of the most elegant ideas in engineering. Heat transfer, whether through a flat wall, a cylindrical pipe, or a spherical shell, can always be reduced to a thermal resistance circuit. The temperature difference drives the heat flow, just like voltage drives current. The thermal resistance opposes heat flow, just like electrical resistance opposes current. Here's the complete picture we've built today. Heat flows in 1D, 2D, or 3D, and we simplify to 1D whenever possible. In steady state, temperatures don't change with time, so heat flow is constant. Fourier's law, Q is equal to K times A times T1 minus T2 over L, the master equation. Conduction resistance, R is equal to L over K times A. Convection resistance, R is equal to 1 over H times AS. Add resistances in series to get total resistance. Q dot is equal to delta T total over R total, just like Ohm's law. Overall heat transfer coefficient, U is equal to 1 over A times R total. Once you understand thermal resistance, heat transfer becomes simple. The same logical framework works for any geometry, flat, cylindrical, or spherical, and it all maps directly onto the circuit analysis you already know. This is the power of engineering thinking, finding the universal pattern underneath the complexity. If you want to master engineering concepts like this, clearly, visually, and deeply, subscribe to Academic Engineering and turn on notifications so you never miss a lesson. Every video on this channel is designed to give you the understanding that textbooks often skip, not just formulas, but the intuition behind them. Thank you for watching. I'll see you in the next one.